Welcome back. Of course, today we're going to start on our next topic. Now, this is the last topic before the midterm, which is going to be arrays. We will talk about debugging, but that's more of a tool, a tool that you can use for your future programs rather than something that's going to be in an exam. Today, after I get home today, I will post to Piazza the details about the midterm that's happening in 2 weeks from today. Basically, it's going to be take home. It'll be released in the morning at about 10 a.m. You'll have until midnight. It'll be very, very similar to what you've done as far as assignments go. So I'll post that later on today. Of course, it is 10% of your grade. No collaboration is allowed on that, unlike your assignments where you can team up with somebody. And of course, if you ask questions on Piazza, we'll try to answer, but we won't be as as forthcoming with answers as we would do for labs, of course, or an assignment. Okay. So what are arrays? Well, it is actually really, really rare to deal with only one piece of data. It is rare to only deal with one number or one character, right? Certainly, or one piece of data. Instead, collections of data are used to store, of course, multiple instances of those things, right? In C and Java, to an extent, we use arrays to store collections of similar things, right? In other words, things of the same type, right? And when I say type, I mean integers, I mean doubles, I mean characters or strings in Java. You can't, in some programming languages, you can have what's called a mixed type, meaning that you have an array that can hold integers, and it can hold strings, and it can hold doubles, right? PHP, for example. JavaScript, I believe, allows you to do that. Those are dynamic programming languages, but both in C and Java, if you have an array, that array only holds one type. It only holds integers, or it only holds doubles, or it only holds characters, or something like that, right? In general, arrays have a single name, that is identifier. Right? And if it's numbers, then you'd call it numbers. If it's a bunch of IDs, you'd call it IDs. If it's just a generic old array, well, A or ARR or something like that, right? You can access individual elements using an index. And you've somewhat done this up to this point with command line arguments. If you want the first element, it's at index 0. We call that 0 indexing, right? The first element is at index 0, right? This is called 0 indexing. The second is at index 1, right, etc. The last, assuming it has n elements, is at index what? N minus 1, right? One short, basically. Indexing is done via square bracket syntax. And again, you've seen this too. If I've got an array called ARR, then I put the name, and then I put square brackets, and in that square bracket, I provide the index that I want to access. So the first one would be at ARR sub 0. The last one, if you know that it's of size n, would be at or ARR sub n minus 1, right? Or in general, if you have an index variable, you of course can use it to index the ith element, right? This is the ith element. Right? So arrays are supported in both languages, but there is a little bit of a difference with C and in Java. The big difference is C allows you to use static arrays. We'll look at them, and then you should forget about them because you don't want to use them. In fact, Java doesn't even allow you to have static arrays at all. Then in Java, the other difference is that arrays are great. You can use them just like you would in any programming language that allows them, but there are much better solutions. There are lists, there are sets, there are maps. These are called dynamic data structures, dynamic collection data structures that allow you to do a whole lot more than just regular old arrays, okay? So let's talk initially about arrays in C. Right? And again, we'll go ahead and start out with static arrays. Right? Let me go ahead and give myself some more room by adding some text at the bottom. There we go. All right, so static arrays. Static arrays in C are arrays that are allocated on the stack. Right? So here's the syntax. And what I'll do is I'll go over here to this visualization, this C tutor. It's actually a Python tutor, but it supports multiple languages. And what I want to do is I want to demonstrate the syntax to you so that you can visualize what it looks like. All right? So I'm just going to go ahead and create an integer array called ARR because you could call it if it's IDs or NUIDs or something like that, right? I'm just going to call it ARR because this is just for demonstration purposes. If I want 5 elements in there, then I provide a size 5 here. Now this is an array that can hold 5 elements. It indexes from 0, 1, 2, 3, 4, right? I can't do that, so I had to go out of order there, sorry. All right, let's go ahead and actually play around with it. So I'll go ahead and create what's called an idiomatic for loop, a for loop that simply iterates over the elements. For I starting at 0, I is less than 5, I plus plus. Right? And then I'll go ahead and set the value. ARR sub I is equal to I plus 1. So what are the values that are going to be stored in that array? Well, the first one will have value 1, 2, 3, 4, 5. Right? Unfortunately, it's been kind of slow as of the last couple of days. While we're doing that, I'll go ahead and cut and paste this over here. And, oops, there we go. All right. Well, while we're waiting on that, I called that an idiomatic for loop. Do we remember what idioms are? In regular old language, like, if I say something is a piece of cake, what do I actually mean? That it's easy, right? But if you were to translate that to another language, like Spanish, and you told something was a piece of cake, I have no idea what the Spanish would be, but they'd look at you like, what are you talking about, right? They have their own idioms. They have their own colloquial metaphors that they use. If you try to take a Spanish idiom and you translate it into English, it wouldn't sound good either. That's why you don't translate those things, you transliterate them. This, in the context of coding, well, coding is a language, so we also have our own idioms. This idiom here is a canonical for loop that simply iterates over the elements in a collection. Right? Wow, it's really taking long today. All right, there we go, finally. So I've got my stack over here, right? What else do I have over here that we haven't looked at yet? A heap, right? So what images come to your mind when you say a stack and a heap? They're both, piles of things. But a stack of dishes, is a very well organized thing that restricts how you can do things, that you can take it off the top and you can put it on the top. But what does a heap bring to mind? Just a big pile of stuff, right? You throw it on top of the heap and, well, it might end up on the top or it might trickle down to the bottom or somewhere in between. If you need something, okay, just go ahead and rummage through that heap of stuff because it doesn't matter if it falls over or whatever because it's still just a big old pile, right? So these are also memory areas in a computer, in a program. A stack is a very organized but small area. A heap is a much larger chunk of memory, but it's less well organized. So there's a trade-off there. With a stack, if I create a static array here, that means that it is allocated over here on the stack, right? So next, of course, it'll allocate on the stack. And what I want to do now, and I was maybe regretting this because I wanted to go back and forth. I was hoping that it was going to be quick. Function void foo. What would happen if we worked with that in another function? So hopefully it'll be much quicker this time. But imagine what's going to happen here. Main is going to call foo. What happens when foo is called? A new stack frame is created. and that array will exist in that stack frame. What happens when we return back to the calling function main over here? What happens to that stack frame on top? It gets popped off the top and thrown away. Does this array exist anymore? No. Right? So one consequence of this, since it's allocated on the stack, since the static arrays are allocated on the stack, they are destroyed. They exist inside stack frames. Those stack frames are destroyed when the function returns. Right? So one consequence is we'll never be able to create an array and return it from a function if we're only using static arrays. Another consequence is, remember, the stack space is small. Right? How small? We're still waiting on this. So let's go over to CS50 here. Right? ulimit, I think it is, limit A. I'm on CS50 IDE here, which is an Ubuntu Linux Docker instance, basically. And so there are limits to memory, right? What is the limit here for my stack size? 8,192 kilobytes, right? So that translates to roughly 8 megabytes, right? How many integers is that? Well, if each integer takes 4 bytes, right, and I've got 8 megs, right, I can do about, what, 2 million integers? So what if I did something that was more than that? Int array of, say, 10 million. 1, 2, 3, 1, 2, 3. Right? And I want to make sure that the compiler is not just throwing this away because I'm not doing anything with it. So let's actually do something with it. 1 million minus 1, I'll set that equal to 42. I'll set array sub 0 is equal to 101 or something like that. And then let's actually print it out. Printf, the last value is %d and the line, ARR sub whatever this is, 10 million minus 1. There we go. All right. So what's going to happen here if I try to compile this and run it? Well, the compiler is going to be fine with it. Right? But what have I done? I've got 8 megabytes here, and I've tried to allocate 10 million integers, which is a little less than 40 megabytes, right? 10 million times 4, 40 million. That's 40 million bytes, but 40 megabytes is actually slightly more than that, so it's slightly less. But it doesn't matter, right? 8 versus 40, right? What happens when you stack your dishes up too high? They fall over, and it results in, here a segmentation fault, but it's also called a stack overflow, right? So already we've reached the limits of static arrays here. And again, finally, here we go. Let's go ahead and visualize this. What happens when we call foo? There's main, right? That's the program's stack frame for main. Here, the program stack frame is called for foo, or is created for foo, and I can fill it up all I want, but I can never return it. Why? Because when I return back from this function, it gets destroyed. So, and attempts to try to access that, by the way, are undefined behavior. Remember what it was called when we started screwing around with the stack? We saw that error on CS50, right? The stack smasher. Right? If you start to screw around with your stack of dishes, then at least on the CS50 IDE, it said, no, you can't do that. Right? Maybe we didn't do that. Let's go ahead and try it now. Let's go ahead and create 100 integers. And let's look at the consequences of accessing something that doesn't exist. ARR sub 100 is equal to 42. Uh-oh. Or ARR sub something else is equal to 101. So is this okay? No. Why? It's of size 100. It runs indices from 0 to 99. This is one beyond. Well, you've fallen off the edge of your array. You can also fall off the other edge of the array. Right? And the compiler is probably okay with that. Right? But what happens when I run this program? Oh, come on, really? All right, fine. I'll go 2,000, 20,000. There we go. No, segmentation fault there. On that line right there, I'm absolutely certain of that. Let's go negative 100. You should be able to detect this. You were detecting this the other day. Whoa, really undefined behavior. Really? Ah, darn it. It resulted in, well, maybe it's compiling it away. Printf %d. Maybe the compiler is getting rid of it because it's realizing, hey, you're not actually using that stuff, so I'm not actually going to allocate that stuff for you. Nope, okay. I'm accessing memory that belongs to, I'm corrupting my own memory, basically. Here's my stack, here's the dish, here's my array, and here's my dish way down here that I've jumped negative 100, right? And I've pulled the dish out from way down here. What's going to happen to all my dishes? Hopefully it would result in a segmentation fault, but in this case, it simply just results in, well, I'm corrupting my own memory, basically. And it's fine with me doing that. Yeah, go ahead.
What are the consequences of that, I guess?
Once you have one undefined behavior, then the rest of your computation is questionable. Cross your fingers and it could end up okay, right? It's okay to corrupt your own memory, to do whatever you want with it, right? But you can't expect it to be correct. There is a, I meant to look it up, but I forget what it is. There's a C-compliant compiler out there that's kind of a joke, but also just to remind people of the consequences of undefined behavior. Basically, they wrote a compiler that completely conforms to all of the expectations, completely conforms to the standards, but with their own addition that any undefined behavior results in an immediate deletion of all of the entire hard drive, right? So I don't know if there's another analogy, but well, I guess if you're a tightrope walker or something like that, right, and you put a lava pit under you instead of a net, right? I absolutely have to be 100% correct when I'm walking this tightrope, right? It's not something that you would do in practice. It is a kind of a thought experiment of undefined behavior is undefined behavior. Anything can happen, including the meltdown of your hard drive. So
what do you assume happened there?
I assume that I'm just corrupting my own memory. I'm going down and corrupting the main function's memory space somehow, or I'm corrupting program code. That's how you can do code injection, by the way. If you are able to change the contents of memory, then, well, what's stored in memory? Program code. And if you can change the contents of the program code and manipulate that, then you can change what the program does so that when it returns back to that program code, you can make it do whatever you want, right? Now, usually it's you do things much easier that you change. If you can change the contents of memory, you keep your code over here, your malicious code over here, and then you change the return address that don't return back to main, return back to that function over there and start executing this code, right? And that's how you break security stuff. Buffer overflows can result in that. Direct memory manipulation, stuff like that. Hopefully, it ends up with a segmentation fault, or as we saw the other day, maybe it was in the main section, we saw an error message come up that said it was a stack smash detected or something, and then it killed our program because we were screwing up our own stack space. Right? But apparently, this is not going to be as nice of a demonstration. Oh well. All right, so remember the stack space is small, say only 8 megabytes, right? So allocating even moderately large arrays, right? This, by the way, 8 megabytes is not big data. If you go back, 30, 40, 50 years, maybe not even 30 years, 8 megabytes is big data. But if you go back 45, 50 years ago, yeah, 8 megabytes is big data. It's not big data anymore, right? Even allocating even moderately large arrays will result in a stack overflow. Right? Not only that, but in Java, static arrays are not even possible. Thankfully, You cannot do anything on the stack space in Java. Int array, so 10, right? Nope, you can't do that, right? I can't do the same thing that I just did in C of now set the first one equal to 42, arrays of 9 is equal to 101 or whatever. It's not going to allow you to declare something like this, okay? So there are no static arrays in C, or sorry, in Java, right? So what's the solution? The much better solution is to use dynamic arrays, right? Dynamic arrays are dynamic arrays. Forgive any misspellings, I usually correct them later on. Are allocated on the heap, right? The heap is a much larger, but less organized chunk of memory. In fact, I'm going to run the same utility that I ran over here, ulimit, and heap memory is basically virtual memory, and it's telling me that it's unlimited, right? Well, it's not really unlimited. It's probably, the addressable space is probably several terabytes, but ultimately you are limited by your physical computer. Virtual memory, you may only have like 8 gigs of RAM, but you can still store stuff in virtual memory that instead of storing it in RAM, it writes it out to disk and then loads it back up into RAM as needed. That is an expensive process. In fact, if you do that a lot, it's called thrashing. And so that's why that's why it's if you use a lot of memory and start using up more of the more than can be stored in main memory, you're going to start doing a lot of thrashing. And then it's disk, and if it's a physical disk, whoa, that little needle going back and forth is super, super slow. If it's SSD, of course, it's going to be a little bit faster, but even then, it is nowhere near as fast as main memory, RAM, right? A bunch of electronic signals. So even though it says unlimited, it's effectively limited by whatever address space or whatever or hard drive space you have. But you're not going to run out for all practical purposes, as long as you are not intentionally stealing all the memory, right? And you can do that, or unintentionally steal it. Let's go ahead and, well, actually, no, let's talk about how you do this first. In C, you allocate memory on the heap by asking the operating system for a chunk of memory, right? You ask for a chunk of memory using the how's that go? Yeah, memory allocation. There we go. I was able to highlight that on the fly. Awesome. Markdown. Memory allocation function, right? Well, you can tell from what I highlighted there, malloc, it's called malloc. Right? And it looks like this, void star malloc, size t, I don't know what, n, let's say that's what it is. That's what, that's its signature. So there are a couple of new concepts here, right? First of all, what is void star? What is that? Where have we seen the star operator before? Pointers, right? This is a void pointer, right? It's not an integer pointer. An integer pointer can point to a location that stores an integer. It's not a double pointer. A double pointer can point to a location that stores a double. What is a void pointer? It's not a pointer that points to a void, right? The empty abyss that you look down and it looks back at you, right? Instead, it is a generic pointer. Is a generic void pointer that can point to any raw memory address. Right? It doesn't necessarily point to a memory address that holds an integer. It doesn't necessarily point to a memory address that holds a double. It just points to a memory address. How you use that memory is up to you, right? Size t can simply be seen as an integer, right? For all intents and purposes. You end up asking for n bytes of memory. Right? So if you want, something to hold 10 million integers, Okay, well, each integer costs me 4 bytes, and so I need 40 million bytes. Right? That's your number that you ask for. And it says, okay, here you go. Or it says, no, I can't do that, and so it returns some special value. Right? So upon success, malloc will return a valid pointer to a memory location that you can start using. Right? Upon failure, what could it return? What's the only pointer that we know is bad? Null. Upon failure, it returns null. Right? So you can check, did I request too much memory? Right? Did I don't know, let's try it here. We'll come back to it after we've looked at the full syntax here, and let's try to request, I don't know, 50 terabytes or something, right? Something outrageously large, and we'll check and see if that actually works on CS50 IDE. I have no idea. But upon failure, it returns null, okay? When you receive the pointer, you should cast it to whatever type of pointer you want to use. For example, you would cast it to int star if it is an integer array, or double star if it is a double array, right, etc. Right? Now, let's look at a full example here, and to do that, now I'll go over to the CS50 IDE. So let's go ahead and create an integer array here. I'll still call it ARR, right? I need a pointer to hold that memory address, and I'll call malloc, okay? Now, again, the last things first, right? Since we read left to right, but it operates right to left. I'm going to cast this as an integer pointer. Remember, malloc returns a generic void pointer, right? Like that. I want it to become an integer pointer because I do want to point it to a memory location that contains a bunch of integers. If you don't do this, then, well, I need to be very careful here because there's a technical issue I don't want to get into, but basically, if you've got a pointer, a raw pointer, a void pointer, it's pointing to a memory location. Where is the next item? If this is the first item in the array, where's the next one? I don't know. How many bytes does this thing take? Because if it takes 4 bytes, well, then it's 4 bytes away. And then the next one is 4 bytes away from that. And the next one is 4 bytes away from that. But if it's a void pointer, I have no idea how much memory each one of those things takes. So by casting it as an integer pointer, now I do know. Integers are 4 bytes. Me being the compiler, by the way. Now the first one is at this memory location. The next one is 4 bytes away. The next one is 4 bytes away. The next one is 4 bytes away. If this were a double, doubles take 8 bytes. And so you know that, and I've run out of hands now, but the first one is right here, right? And then the next one is 8 bytes away. Then the next one is 8 bytes away, 8 bytes away. And that's why we do this type casting right here, so that it is forced to become an integer pointer. If we treat it as a raw void pointer, then it's byte addressing. And you essentially, here's the first byte, the first 8 bits, here's the next 8 bits, here's the next 8 bits. You'd have to get 4 of those things, put them all together, and then treat it like an integer, which is really, really inconvenient. Right? How many bytes do we want? All right, remember, we're not asking how many integers we want. Say that we wanted 100 integers, something small. Right? I want 100 integers. Do I pass in 100? Nope. How many integers, how many bytes does an integer take? 4, so 400. I can do that, but I don't like doing that math. Especially if I take this code over to another system where an integer is not 4 bytes. For some reason, it's only 2 bytes. That's actually the C standard. It just says that an integer has to be at least 2 bytes. There's some super weird systems where it's only 3 bytes, right? Maybe in the future, when we've got much bigger computers, all integers are now 8 bytes. I want to make sure that this is future-proof. Well, you can go ahead and say that n times 4, but again, it's not always 4 bytes. There is another utility called size of. Size of gives you how many bytes an integer takes. You might remember this from lab 1 or lab 2 or something like that, where you had to fill out a table of how many bytes each thing takes. If you looked at the code, how are we achieving that? We were simply calling size of here. Right? If it were a double array, well, then how many bytes does a double take? How many bytes does a char take, right? Et cetera, et cetera. Now I've made my code interoperable. If I take this over to a system, a weird system that everything is 5 bytes for some reason, then it will still compile and it will still work as expected. Okay? There. Once it's allocated, I can start treating it like a regular old array. Set the first value to 42. Set the last value equal to 101. Print them all out. For int I equals 0, I is less than n. There's that idiomatic for loop again now. I++, printf, array sub %d is equal to %d and the line. And that's going to be I and array sub I. Oops. There we go. And GCC, lay that out. There we go. Last one was set to 101. The first one was set to 42. All right. All of the rest of them are 0. Don't bet on that. All right. So some observations here. You can use size of to determine how many bytes each type takes. All right. By default, the default no default values are defined in C. Right? If I take this code over to the C visualizer, it might just be a bunch of poop emojis, unfortunately. But if I take this over to the CSE, I cannot guarantee that these will all be zeros. Right? It is completely compiler and system dependent. Right? If you want to guarantee that they're all zeros, there's another memory allocation called calloc. Calloc. Right? It works slightly differently, and there's also one called realloc if you want to reallocate memory. But the key difference here with calloc is that it does fill it up with null bytes. Allocates memory for an array, blah, 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 and the memory is set to 0. Right? So if you do want to initialize an array of zeros, then you can use calloc, but it is a different way of writing. So you have to specify the number of members. So here you don't do the multiplication; you let it do the multiplication for you. And this will end up being 100 integers. How many bytes does each one take? Well, then that's the second argument here. So it is slightly different. But if you do want to use that, then you can. I'm only generally going to cover malloc here. Right? It could be zeros. It could be garbage. Right? You should initialize the array properly. Now, in Java, the default values are 0. Hey, nice. All right. You will not have garbage in Java. Okay. Let's go back over here and let's experiment with what I wanted to do before. Let's try that 10 million. 1, 2, 3. There we go. And we can see that, of course, this is going to work. Just a second. But of course, it's going to try to print 10 million things. I'm not going to let it. It's not stuck in an infinite loop. It's just doing a lot of work. So 10 million, that's fine. 40 megabytes, nothing. Yeah.
So like you said, the default value in Java is 0.
Yep.
Does that mean that dynamic arrays work in Java, but not static arrays?
Correct. And we'll get to that here in a second here. So I don't know, give me something outrageously large. There's 1, 2, 3 million, billion, trillion. That's a quarter of a terabyte. So 2.5 terabytes, 25 terabytes, right? 250 terabytes. Let's go ahead and try that. Oh, I need to save it first, maybe. All right. Okay, there we go. You asked for way too much there. 250 terabytes, no way. How can you check for that? Well, if array is null, then we know that it failed. Printf, you can't do that. No one has that much memory. I don't know, is there a, like supercomputers, of course, would have that much memory. If you go over to the Holland Computing Center, that's nothing. Individual hard drives, of course, are going to be limited to what? Can you get a 10 terabyte hard drive now, probably? Can you get larger than that?
Maybe in like server applications.
Okay, well, then even then you'd get smaller ones because you have to replace them when they go bad. So it's much easier to replace lots of smaller ones, and individuals go out. I don't know. I don't know if anybody has something that big. But you can see here that it returned null, and that's why we got our segmentation fault, because no way is malloc going to give you that much memory. All right. This is actually probably overflow, and we're asking for a negative amount of memory anyway, which can also happen. Negative 10 times that. Ooh. Okay, it's not even going to let me do that? Sweet. Whatever. I don't know why it's not letting me do, the compiler shouldn't care about that, but okay, nice, good compiler. If you can pet your compiler, then great, because it recognized, no, you can't do negative, you can't ask for a negative amount of memory. All right, good. So Java, you can't even do that. You can't do static arrays. How do you do this in Java? Dynamic arrays in Java. Right? So Java doesn't have malloc. Right? Instead, you use the new keyword. Okay? So I'm going to go ahead and go over here to my demonstration in Java here. And of course, there are no pointers, so you're not returning a pointer from a function call or anything like that. There's a declaration. Int array with the square brackets, no size given. Right now, this is an uninitialized array. This is actually null. It's not pointing to any particular array. If you want to point it to an array of size 10, then you have to say new array. Well, what should be in this array? A bunch of integers. How many of them do you want? 10 of them. And that's the syntax for doing it in Java. Array, so now you can use it like a regular old array and set the first one to 42, array of 9 or whatever equal to 101. Yeah? The static array, if you could do that in Java, would be like this. You don't call a new keyword. You provide the size here without the keyword new. Right? You can't even do this. This is a syntax error. No. Right? But this is perfectly fine. No size, and then to initialize it, you call new int of size 10. Right? Now here, what happens if you try to access stuff that doesn't belong, that doesn't exist? 42 and array of 10 is equal to, I don't know, 90. Right? It's perfectly fine with that as far as the compiler is concerned. But if I run this, of course, I'm going to get an index out of bounds exception instead of a segmentation fault, okay? Or a stack smashing event or something like that. Why? Because Java actually does the bookkeeping for you, right? And we'll talk about that here next. So I want to make sure that I've got it. Here we go. How would I do this for doubles, by the way? A double numbers is equal to new double, and how many do you want? 20. Right? After that, of course, you can use them just like regular old arrays. Okay. So, example. I'll make sure that that's in the notes here, Java. There. Okay. All right. Bookkeeping. Right. In C, or C has manual memory management, meaning it is on you, the programmer, to keep track of the size of the arrays you create And well, here, let me go ahead and make, it is on you to, one, keep track of the size of the arrays you create. Pass that size to any function or functions that you pass an array to, right? And ultimately, ensure that you do not access values outside the array's range, right? And finally, it is also on you in C to clean up after yourself. Once you're done using something, what do you do with it? You put it away, right? Or once you're done using the whiteboard up here, what do you do with it? Erase it, clean it up, right? With respect to memory, that means giving it back to the operating system, because C, remember, how do you get the memory? You ask the operating system for it, and the operating system says, okay, here you go, right? Well, okay, I'll use it, I'll do all my number crunching or whatever I need to do. Now I'm done with it. What do I do with it? I don't just throw it away. You can't delete RAM any more than you can download more RAM. So it's not actually, being deleted or anything like that. It's just being wasted. You're holding on to memory that you no longer need. What do you do with it? You give it back to the operating system, right? You need to give it back to the OS once you are done with it, right? To give it back is to not destroy it or delete it or anything like that, but to give it back is to use the free function. And to do that, all you need to do is call free, and then whatever array you created like we did before. The array that we had before was ARR. You simply call free and give it that. Now, that's a signal to the operating system that there's this chunk of memory over here that I no longer need. You can have it back. The operating system is free to do with it whatever it wants. It may claim it immediately and give it to another process. It may claim it back and put it into a pool to give it back to you if you ever need more memory. That's its business. Once we've freed it, we cannot access it anymore, right? So, once freed, that memory no longer belongs to us. Attempts to access it are undefined behavior, right? You can't erase the whiteboard and say, oh, I didn't mean to do that. Right? If you didn't mean to do that, you shouldn't have done that. And if you wanted to save it, then what you should have done is take a photo with your phone or something like that, and save it to disk or something if you really need that data. Attempts to free memory that doesn't belong to you are also undefined behavior. And this, I've seen it before where students get into trouble because they free something that they freed before. So you can't free something twice. You can't erase the whiteboard twice, right? And if you do, then it will end up being probably a segmentation fault or something like that. So let's go ahead and take a look at our example over here. I'm not going to print here. I'm not going to do 1 million, but I'm going to do 100. Right? There we go. GCC, and we'll run that, of course, and we're setting the first one again to 42, the last one to 101. How do we clean up after ourselves once we're done? We can free the array. Oh, I didn't mean to do that. I actually wanted to access that first value there. I want to get the first value 42 because I forgot what the value of 42 is, right? Let's try that. Note here what I've done. I freed the memory, and then I try to access it again. Right? Ah, really? You're going to let me do that? Oh, thank you. Excellent. Excellent point that it's not 42. So it's been erased from existence, right? The operating system was free to do with it whatever it wanted. It probably nulled out all of our memory and then left it in the pool for our program. Let me create something larger, maybe 10,000. I'm trying to get it to seg fault out. Certainly this should happen. There. Oh, nope. It's just garbage values, right? 10,000, 100,000, but I don't want to print it anymore. There, now segmentation fault. So why was it working before and then finally we get a segmentation fault? Because again, that undefined behavior, anything goes, anything can happen. It could work. It could have bad values. It could result in a segmentation fault. What actually is going on under the hood is when I was only requesting 100 bytes, it's inefficient to just give you 400 bytes. Instead, it allocates pages, and pages usually are like 4K or 8K or something at a time. And so it'll give you an entire page. Even though you're only going to use 400 bytes of that page, a whole bunch of extra memory was given to you because it's not going to waste its time with small change. So what it does is it gives you an entire page, and as long as you stay within that page, you're good to go because it's your memory, right? The operating system doesn't care what you do with it. So that's your business. But if you go beyond that page, right, and get into other programs' memory, that's when it results in a segmentation fault. Okay? So, and then the last thing I wanted to show you is what happens if you free it twice. So we won't access it instead. Free array. Hopefully this will be a segmentation fault as well. Oh, come on. I have to just make it big. I have to make it big for it to work. There we go, right? Because I need to request several pages to actually get it to screw up, right? Attempts to free something twice are undefined behavior, in this case, a segmentation fault. It's going to say, you can't free up that memory. It doesn't belong to you, right? So segmentation fault. Yeah?
So you can only really free something if it's if it's big enough. Otherwise, it's just.
You can only free something if it belongs to you, and if you're done with it. If you're not done with it, don't free it. Right? Don't erase the whiteboard until you're done using the whiteboard. Right?
So what does size have to do with whether it's a segmentation fault?
Because it's bleeding into other people's memory at that point. A small amount of memory, it's probably just going to let you continue having it for a while because the operating system doesn't want to waste its time with 400 bytes, right? It'll say, all right, you go ahead and keep that until the program is done running, and then I'll clean it up, right? Just like, I don't know, instead of picking up one piece of trash, every 5 minutes, I'll just wait until the party's over, and then I'll pick everything up at once, right? So it would be inefficient to go around. You wouldn't be able to enjoy the party because you're always picking up trash throughout the thing. Yeah, it's clean at the end, but did you waste your time over the long term, or just concentrate your time at your resources at one time? Right? Okay. All right. So failure to do so. Failure to clean up memory after you are done using it may result in a memory leak. Right? A memory leak is where you just keep asking for more memory and then you hold on to it. Give me another 50 megabytes. Give me another 50 megabytes. Give me another 50 megabytes. Now think about consumer applications like, say, a web browser. Firefox used to be notorious for this, which is why I switched over to Chrome for many years, and then Google started being evil again for once, and so I switched back to Firefox. Because Firefox has fixed all their problems. But Firefox is notorious for memory leaks. You leave it open you open up one tab, and it grabs a chunk of memory. It has a memory leak, so it doesn't give it back. You open up another tab, and it keeps on, even though you've closed that tab, it doesn't give the memory back, and so it keeps on holding on to it. Well, if your program is holding on to larger and larger chunks of memory, that means that there's less memory for other processes. It means that that's going to have to be thrashing back to disk and loading it up into RAM, random access memory, back and forth, right? And eventually it just slows your entire computer to a halt. You need to make sure that you are being good stewards of your memory. Clean up after you're done using it as quick as possible, right? You need, in C, you need to be good stewards of your resources, right? Again, failure to do so would result in undefined behavior, segmentation fault, memory leak, a whole bunch of other different things. Java has no manual memory management. Right? It is all taken care of by the garbage collector. Java garbage collector. Right? And what we mean by that is once an array or object is no longer in scope, in other words, no piece of code still has a reference to it, it is eligible for garbage collection. Right? At certain increments, the JVM, the Java Virtual Machine, will reclaim memory automatically. You don't need to worry about a thing, right? Mostly. For every rule, there is an exception, right? There are some instances in which if you hold on to the memory, then you can cause memory leaks in Java. I won't give a demonstration here, but I think if you're in your lab next week, I don't know if we have a memory leak in Java. Yeah, we have a memory leak in Java. All you're doing is basically claiming memory and then never letting it go. But once you've let it go in Java, it takes care of it for you. It's like a Roomba that automatically goes around and picks up the garbage automatically. You don't have to worry about it at all. Right? A lot of modern programming languages have this. PHP, JavaScript, depending on the interpreter, they'll take care of automatic garbage collection for you. But in C, you are with great power comes great responsibility. Right? In Java, you don't have access to the low-level memory. You can't manipulate memory directly in Java. The Java Virtual Machine takes care of all that for you. But that's the price you pay. The benefit that you get is by not having to worry about memory management. You don't have to delete this thing over here. Right? I'm done with it. Okay. Don't worry about it. The JVM will take care of it for you. And you don't have to, there is no cleaning up. There is something, you'll probably read a tutorial at one point where you'll see something like system.gc. What do you think GC stands for? Garbage collection, right? It runs the garbage collector. You can manually, or it appears at least, that you can manually run the garbage collector. But if you read this, it doesn't actually say that, right? In fact, standard blah, blah, blah. Portion of the means loading, it's not even telling me this. No, I want GC. There we go. There, excellent. I'm glad that it's telling this. I don't know if you can read it up out there. It's kind of small, but calling the GC method suggests that the Java Virtual Machine expend effort towards recycling unused objects. In other words, it's just a suggestion. It's not actually going to run the garbage collector if it thinks that it doesn't matter. If the garbage collection say, well, if the JVM says there's only 50 bytes that I would clean up, I'm not going to do it. I don't want to waste time and CPU cycles on cleaning up this memory when it's only 50 bytes worth. So I'm not going to do it. Right? There are very sophisticated garbage collection algorithms that are being executed under the hood. Let them do their job. Right? Don't do something like this. In fact, explicitly it says that you can't. It's just a suggestion. It's free to ignore you, right? If there's not enough to clean up. In fact, in this case, there's definitely not enough to clean up. There's only 40 bytes here. There's only 80 bytes here. No way is it going to clean up, right? And there's no way to tell whether or not it did clean up unless you're using some sort of a profiler. Yeah?
So how would we know what it would clean up and what it wouldn't?
You don't want to have to worry. The reason that you're using Java is because you don't want to have to worry about that kind of stuff, right? That's the reason that you're using a garbage collected language to begin with. If you do want to worry about that low-level stuff, then you start hacking the Java Virtual Machine, or you use a different language. Right? No, okay. And people can do that. I mean, this one, I think I suggested to at the beginning of the semester to install Sun used to own Java. Now it's Oracle. Oracle's Java Virtual Machine and JDK. There are alternatives out there. OpenJDK is an alternative implementation of Java and the Java Virtual Machine that uses completely different code. You can make your own. Here's the Java specification. Go ahead and write your own JVM, and you can do that. And then you could say that I'm going to change that system.gc to be a rule instead of a suggestion. I don't know why you'd do that, but yeah.
And then, but we would have to worry about this and see.
Yes, absolutely. And you'll see this in Lab 7 next week, where we intentionally cause a memory leak, and then you can start to, in fact, I can show you a quick preview here. If I don't do, let's go into a for loop to do all this stuff instead. For int I equals 0, I is less than, or you know what, I'll just go into an infinite loop, I don't care. While we will go ahead and request 100,000 times 4, so 400K, right? Yeah, 400K over and over again, but never actually use it, right? GCC. All right, fine. Get rid of all this stuff. Now I don't need it anymore. All right, it's stuck in an infinite loop here. I'll kill it so I can actually look at it. All right, it's running in the background. I'm going to look at how many resources it's taking. I don't have enough room to do this though. User, who am I? I should be Ubuntu. All right, fine. Do you see this? Where is it? Nope, free, used. It's running, isn't it? Where is it? Oh, no, somebody killed it already because it took up too much memory. The operating system actually detected that it was taking up too much memory. Quickly, come on. Where is it? Where is it? No? All right, they kill it way too quick. I'd have to do this on CSE. And you'll do it on CSE, but you'll do it on CSE and in your lab next week, right? All right. So, what about, and then also in Java, sorry, to continue with Java here, there's also no bookkeeping. You don't need to keep the size of the array, keep track of the size of the array, of arrays. It is available in arr.length, right? So an idiomatic for loop in C or in Java would look something more like this. Let me go ahead and get rid of all this stuff. And let's go ahead and set the values to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For int I equals 0, I is less than, normally I would have to either hard code this or put this into a variable called n, but I don't have to do that in this case because in Java, the length is stored as part of the array, I++. And then I can say arr sub I is equal to I plus 1. Right? Okay? Array.length. This is called a property, it's set when you initialize this thing. If you ever reinitialize it, of course, it's going to be reset, but you don't have to keep track of it. If you pass an array to a function, that function doesn't have to be told how big it is. And it's not size, right? It is length. Okay. All right. Okay. Any questions so far? We'll come back to some of this, but what I want to do now is show you a little bit of a difference with Java collections. Right? In Java, regular old arrays are terrible. Right? They're just not. They're dynamically allocated, but they're not dynamic enough. Right? There are much better dynamic collection data structures, right, that you can use. Data structures is 2 words. Okay, there we go. For example, lists. Right? And the primary one that you'll use are array lists, right? Lists, right? List is an actual keyword. It's an interface in Java. Don't worry about that distinction. Are ordered collections that use zero indexing, but they grow and shrink automatically as you add or remove elements. Right? To interact with a list or array list, you call various methods on it. Right? You also specify that a list holds a certain type of variable using parameterization. Parameterization, there we go. That's the correct spelling. Right? Let me go back over to my Eclipse IDE here and start showing you what I mean. So the problem here is this array will only ever be of size 10. What if, now I need to store something, now I need to store an 11th object. Can I do that? No, because it's only of size 10. I would have to create a brand new array, copy everything over, and then add that one element in order to accommodate that new element. Or I could ignore all of that stuff and use much better data structures like a list. A list can hold any type that you want. In this case, I'll make it hold integers. If I wanted to, I could have a list that held doubles. Right? So we'll write each of these in parallel. Note here that you do have to bring it in. It's java.util.list. And so up here in the import, I'll get rid of the unused imports here. Java.util.list is what you need to bring in. Question?
Why the capital integer and capital?
Good question. Well, it's because you can't do primitive types in Java. You can do that in C++, but you can't do primitive types in Java. It has to be objects. And so it has to be big I integer and big D double. You can't use the primitive types. I'll go ahead and go with numbers over here. Right? You still give it a name. You can call this an array, but it's no longer an array, is it? It's a list. So my numbers or whatever, right, is equal to a new array list of integers. I don't know, do I have Java 8 here? Okay, that's good. So there's something that you can do. You don't have to repeat the integer over here in modern Java implementations, certainly as of Java 8 or something like that. You can elide it. Ooh, that's a nice 50-cent word, isn't it? What is elision? Does anybody know? In speech. So the example I gave the other day in the main section was, are you going to watch the Husker game when it's on the 24th? Are you going to watch the Husker game? How did I say that? Are you gonna? Right? Is that a word in English? Not a proper word, of course. Right? What did I do? I elided it. I took out syllables because I wanted to speak faster. So properly it should be, are you going to watch the game? Right? Enunciate each one of those syllables. Right? But if you want to, in regular speech, you elide all the time. Every speech does this. Every language does this to some extent, where you elide things. You throw away symbols because it allows you to speak more, faster, but also more fluidly. Are you gonna? Right? That sounds way better than are you going to? Right? It sounds way too proper or something. Right? And so elision is taking out unnecessary things. In this case, it's taking out an unnecessary repetition of integer over here because the compiler can figure that out. You wanted a list of integers. Okay, I know that you want an array list of integers. Right? You can't do list on both sides. Object-oriented programming thing that we save for next semester, don't worry about it. Right? Just understand that you should do it like this. Right? If you want a list of doubles, right, equals new array list. And then, of course, you can put double in there, or you can elide it away. Elide, E-L-I-D-E. Right? Once you've got these things, you can start using them. List dot, I want to add an element. Add 10. List dot, add 20, list dot, add 30. Right? And now 10, 20, and 30 are in there. If you want to add something to the beginning, list dot add. At index 0, add 40 right there. And then let's print it out. System.out.println list. I should have called it my list or something. Now 40 is at the beginning. If you want to add it to an arbitrary index, I want to add it right in the middle somewhere, right? You can do that as well. Everything moves over automatically for you to make room for it. You can't do that with a regular old array, right? Question? Okay, all right. You can also remove things. List.remove. Remove the first element. Right? And once I do that, then I'll end up removing 10 in this demonstration right here. Right? Remove. Right? I can add a list to another list. I can make a list copy automatically. I can do a whole bunch of other things. What else can I do? Okay, my ID is broken. Java list. Here's all the things I can do with a list. I can add, I can get. That's the other thing you would want to do, right? Int x is equal to list.get. Let's get the first element, right? And then print that out. What's the first element in this case? 20 at that point in the code. 20, right? So you can get things, you can get the size. Size. Their size is equal to, now it's not length anymore, it's going to be list.size. And it is a function call, so you need those two parentheses right there, right? And the size is 3. Why? Well, because it holds 20, 40, and 30, right? Way better than boring old static array, or boring old arrays. Yeah?
I would expect that to be the result of like list.length. Like size would be 3.
The size would be, I add 10, 20, 30, so the size is now 3. I add 40, size is 4, but I remove the first one, so now we're back down to 3. I print it out, I've got 20, 30, 40, and 30, and right now the size is 3.
So the size isn't referring to a data size, it's referring
Correct, it's referring to the number of elements in the list. Good, yes. Length would give you the number of elements in the array, not the number of bytes. In the JVM, you don't have to worry about those low-level details. Right?
list.length doesn't exist, or it would be redundant.
Yeah, well, yeah, because it's not an array. That's an array thing. It's a property of arrays. Yeah. Awesome. Things also numbers.add. You can add 3.14. Also, you can do, the compiler is now smart enough to detect things that you shouldn't do. Try to add hello. Nope. Why? The method add of the list is of type the list doubles. Is hello a double? Nope. So it's not going to let you do that. Right? So it does detect no, you can't do that. Right? You can of course clear it out. Numbers dot what is it? Clear. That removes everything all at once. You have a whole list of things that you can do with lists, right? A list of things you can do with lists. You could add another collection. You can clear it out. You can ask, does it contain 10 or does it contain 42? Is this list equal to that list? Can you give me the element at a particular index, et cetera, et cetera. Right? And remove all, and a couple of other things too. Well, I'll go ahead and put this in the notes. Those are lists. Right? And we're only touching the surface here, by the way. You also have something called sets. Right? A set is like a list, but a set is a collection of unordered, unique elements. Right? And those two keywords right there tell you the difference between a set and a list. Is unordered, there is no first element, second element, etc. Right? Instead, there are just elements. You could add things to it, but you can't add it at a particular index because they're not ordered. Right? You can't get the first element, so you can't get 0. So what are we going to? We're going to have to solve this problem next week, right? How do we actually say iterate over a set? And the other keyword there is unique, right? You cannot add more than one instance of the same element, right? No duplicates. So if you add 10, it's in this set. If you add 10 again, it's not going to add 2 10s. It's just going to have that one original 10 in there, okay? Really quick here, since we only have 5 minutes, is set. How do I do this? Integer s is equal to new set, hash set, and then we'll review this on Tuesday. I have to, of course, bring all these things in. They're all in java.util, java.util, java.util. There we go. s.add 10, s.add 20, s.add 30, and system.out.println s. Right? Is it in the same order that I added them in? Nope. Why? Because it's unordered. Right? If I try to add another 10, is that going to work? It's not going to delete the hard drive. It's not going to blow up. It's just not going to do anything. Right? 10's already in there. I'm not going to add it again. Right? So sets are unordered and unique elements, just like math. I don't know if probably haven't taken discrete math yet. You'll probably take it next semester. That's CSCE 235, and you'll go over set theory there. Right? But a set is exactly what you would expect from a discrete math set or setting where you define sets. Sets are unordered collections of distinct elements, no duplicates. Okay? All right, then have a good weekend. Remember that assignment 2 is posted. Assignment 3 is due not this Friday, but next Friday. So we've more than covered everything on that assignment, so you should get started on it now.